Good morning, everyone. Hear me? Oh, there we go. So normally when I'm on a stage in front of a group of people that I don't know very well with a microphone, I'm about to start singing some karaoke. So I'm going to try really hard to not start breaking out into some Neil Diamond songs and stay focused on the technical content, but I'm not going to give you any promises. So as Bill said, my name is Erik Paulson. I work at Intel Corporation in our Fabrics team. I'm here to basically just give an update about PGAS technologies using the OpenFabrics Interface. Before I do that, though, let me flash some legalese at you. Read it really carefully. There's going to be a quiz later in the day. More legalese. OK, so what does this talk about? Again, as I said, this is just going to be a grab bag update from our work in various PGAS libraries within the open source community. And mainly those are OpenSHMEM via the SANDIA OpenSHMEM and GASNet, which is what I've been working on. So we're going to talk about some performance characteristics. We're going to talk about how PGAS languages are changing as time goes on, and how OFI is going to continue to play a part in the PGAS arena. So OpenSHMEM. Just going to give you a disclaimer. This is the part of the talk that I didn't personally work on. My colleague Kayla Seeger and also our colleagues in Intel, James Dyna and Dave Ozog, worked on this half. But I'm going to give you a pretty good rundown of it, I hope. And if not, I'm going to punt to Kayla in the back there, and she can answer your questions. So what is OpenSHMEM? It's a pretty simple HPC communication runtime. And by pretty simple, I mean that I can look at the spec and instantly know what's going on. You have some puts, you have some gets, collectives, and atomics. It's pretty easy to comprehend. So OFI, from the start, has worked pretty well for OpenSHMEM. So one of the big things is that, I know we've probably talked about this before, so I'm not going to hammer you too deeply on this. Our memory registration model, which Sean went into some detail about yesterday, works really well because it's super simple to just expose your entire virtual address space to these applications via OFI. We have a good set of atomics, which I don't need to nail you on. We have some good ways to make small messages go through the network really quickly using our FI inject function. And the reason why this maps really well to OpenSHMEM is because in SHMEM, put operation is blocking only until you can reuse memory. And that's the exact semantic that this FI inject function gives you. I don't think I'm going to hammer you on the rest of these things, but really we want OFI to map incredibly well to PGAS, and we think that so far we've been able to do that. So I just want to throw some performance numbers at you because Kayla presented the more or less rundown of the design of OpenSHMEM at this conference last year. So we just want to let you know how it's working so far. So all these tests were run on Corey NERSC. What we're going to compare it to is SHMEM, and SHMEM is running on the Aries interconnect using the Cray DMAP API. This API was designed for PGAS and really optimized for small messages. And as I said earlier, we're using SANDIA OpenSHMEM over libfabric using the GNI provider. And UGNI, which is the API that drives that provider, it was very much designed for MPI and PGAS and is more suited for large messages. So just seeing some graphs here. I mentioned the FI inject function earlier, and you can see for messages under 4K, which is in this case what a small message is, we see a pretty noticeable bump using the FI inject function. And beyond that, the performance is more or less the same. And for gets, gets block until the operation is actually done, obviously. So the performance is more or less correlating, and we're within 2%, which is pretty great. Looking at some scalability numbers, a little background here, the DMAP API by default has large pages turned on. 2 megabyte pages. So you have two numbers here for OFI. One is just normal. You grabbed it out of the box and ran it. And it's the green line right here. And you can see it correlates more or less to the DMAP line. And then to have a real apples-to-apples comparison, my colleagues turned on large pages for OFI to see how the scaling works. And you can see we got a pretty good bump beyond 64 RPEs. For something like the integer sort, it scales more or less the same, and even above these large numbers, we get a little bit better performance, because in this graph, lower is better. Just to give you some more idea on some systems that aren't Quarry, we're going to show you some numbers that we took running over PSM2 with Intel Omni-Path fabrics. And we're going to compare it to the OpenSHMEM reference implementation, which is using GASNet which I'll talk about in a little bit later, and the PSM2, there's a fly here, get this out, the PSM2 native implementation on GASNet. So this is a great graph because the lines are so close, they're blurring into one unified color. And you can see there's maybe a little dip here, but not much. And beyond about 16K, the performance is more or less the same. And you can see also on the put side, we get a nice little bump here that's incredibly significant. And again, the reason for that is that FI inject function. And it's possible that the SHMEM reference implementation is maybe doing a blocking operation here instead of a non-blocking, which is coming up for this difference. But beyond that, again, very similar performance, really nice lines that we like to see. So I think it was on Tuesday, the gentleman from Rice University was talking a bit about context. And this is some work that some of my colleagues have been very active on. And I just want to give a general overview update of that. So what context is trying to solve is that OpenSHMEM currently is a single-threaded API. And obviously, DK Panda was talking about how multi-core, many-core are a huge thing now. And so that's something we need to address and solve. And so the idea of context is we're just going to tack on another function argument that will allow you to designate which context you want to issue operations on. So you can see here, this is supposed to represent 3 different contexts. The idea is that I can have context A, issue a bunch of puts on it. I can have context B, issue a bunch of puts on it. And I can call quiet, meaning synchronize all of these puts on either context A, context B, or both of them. And so the original idea of this is to enable multi-threading. But also, it just gives us better communication overlap. Even in a single-threaded application, you can still use this to complete some set of operations before you complete another, which just gives us more flexibility with how you write SHMEM programs. And as you'll see, this maps pretty well to OFI and has made life easier for the people who are actually doing this work. So don't get too focused on this implementation. It's not too important. The idea here is our current implementation of SANDIA OpenSHMEM through OFI. We kind of try to optimize for some situations that really, if end users had context, they would be able to do themselves if they needed it. So just for one example of this is that we've split out our implementation into 2 endpoints. And that way, we can complete blocking gets and blocking puts in. Sorry, we don't have to wait for blocking gets to wait for blocking puts to complete. And so the idea that contexts have is we're going to start bundling up some of these resources. So up here, this is an OFI shared transmit context. It basically just represents some hardware entity that can be used to send and receive messages. And what we really would like to see is have each thread have its own transmit context to be able to send messages in parallel. And so we're just going to bundle up some of these resources into SHMEM contexts. So this is what the implementation that some of my colleagues are working on looks like. And so we're going to have multiple shared transmit contexts, which maps to multiple hardware resources. And you're going to be able to just create communication endpoints that do specific things. You can have one that just does puts, one that just does gets. This big box on the right is for backwards compatibility with the current design. It kind of has the full gamut of things that have been in the design so far. So now if a user wants to do one of these optimizations, they can just create their own context and issue them accordingly. Really, being able to have exposure to these transmit contexts is what makes this really easy to work and implement. And as far as I know, there's not many other networking environments other than OFI that really support this. So that is about all I have to say about that. So we're going to switch gears and go to GASNet after I refuel. So what is GASNet? It's a low-level networking API that's meant to enable PGAS languages. Like some of those PGAS languages we'll see in a second are like Unified Parallel C, UPC++, which was on DK Panda's slides, Chapel, which is made by Cray. So it's not an end-user library. It's for nerds like us who are developing these cool technologies. The people who own it is Lawrence Berkeley National Laboratories. So again, here's some of the languages that are using it. Berkeley UPC, Chapel. As we already saw, OpenSHMEM uses it in its reference implementation. And so it has a layered approach where they have a core API, which is basically active messaging API. And on top of that, they have an extended API, which has like RMA operations. It has some collectives. And you're only required to implement the core API, and they provide you a reference implementation. But you have the option to, if let's say your hardware has really good support for collectives or for RMA, to actually override their reference implementation and provide your own functions, which is what most, what they call conduits, which is a GASNet implementation, do. So most relevant networks have native support. OMNI-Path has native support. Aries Interconnect has native support. There's IBV implementations as well. So I have taken over working on the OFI conduit, the OFI-based implementation this year. And so currently the state of support is that we support Intel TrueScale architecture, Intel OMNI-Path architecture, and just normal sockets. That's through the PSM, PSM2 provider, and the sockets provider. Some work I got upstream recently was to enable support for Cray-XC systems over the GNI provider, but that's still experimental, hasn't been validated very much yet. Hopefully we can move that out of experimental soon. And also, theoretically, the BlueGene provider should also support this, but I don't have access to one of those systems, so I haven't been able to test it yet. If anyone wants to test it for me and let me know if it has bugs or not, I'd love that, and I'd appreciate that. So what do you need to support for GASNet? You need to support reliable datagram endpoints. We'd really like it if you have Mr. Scalable to enable just registering your entire virtual address space easily. There is support for MR Basic, and as Sean mentioned yesterday, these are getting reworked in the next version of OFI, so there will be some more updates based on that. You know, you need to be able to send and receive messages, and we'd like to be able to use multi-receive, which lets us cut down on the number of function calls you make when we're reposting message buffers. Something really cool that the OFI WIG has been working on is supporting utility providers, which Sean Hefty talked about a bit yesterday. That means that through one of these utility providers, support for GASNet on a platform like Verbs that doesn't have RDM endpoints will basically just come for free, hopefully. And that'd be really great to have. So kind of just some work that's been done in the past like 6 months on this. Really, the OFI implementation hadn't had a really thorough code review, so I sat down with LBNL, and we did like a great 3-hour pick apart this implementation. And a lot of it has just been like pretty mundane bug fixes that I won't bore you with. Again, I said earlier that we got the GNI provider working experimentally. Basically, some of the big things is I set up a framework to be able to do provider-specific optimizations. And that's just because not all providers support the same thing. Hopefully, as the time progresses, we'll start merging onto something that is more converged for all the providers. Also, I've done some threading improvements, just gotten rid of some locks and moved to using the FI thread-safe model, which should hopefully let providers have maximum levels of concurrency within their implementations. And also just accelerated some certain messaging pathways within GASNet. So I'm just going to throw some numbers at you on GASNet. These are just going to be some point-to-point micro benchmarks using some Xeons. So looking here on the left for put latency, you see there is a little bit of a performance decrease with GASNet over OFI. But beyond 16K, the difference is, there's basically no difference. And I'll get to that in a second. And same thing over here for bandwidth. Below 16K, there's a little bit of a performance decrease. But beyond 16K, more or less the same. So why is that? What's going on here? So we're comparing this with the PSM conduit, which is the native implementation through the performance scale messaging API. And they're leveraging a little bit different completion mechanism than we are. Within their API, they have an active messaging API, which is what we're using to chunk up these data payloads and transfer them over the wire. And so they have this completion function, which is callback that runs once the remote execution of the remote handler completes. And this is able to give their implementation a little bit better latency and reduce some of their overheads. But the issue is that it doesn't report error or success codes. Not to say that a completion function couldn't, it's just that this specific one doesn't. So our provider implementation for PSM2 is doing some error checking, so it's not leveraging this. And it's also just kind of doesn't semantically fit OFI. This is kind of an example where if we had a native OmniPath provider, we may be able to map this a little bit better than through PSM2, which is what we're currently doing. And that's something we're kind of investigating as time goes on to see if it will make sense for us to tackle. So kind of one of the themes of this conference so far is that our environment is changing a lot. And so GASNet is also changing to meet the demands of exascale. The next version that LBNL is working on is called GASNet X. So what GASNet X does is it kind of solidifies some of the experimental features that were provided in the last version of GASNet. And that's the vectored index strided operations, which you've seen some presentations about on other platforms already, and also some collectives and independent operations. I'm hoping that as time goes on, we'll have better support for some scatter-gather list operations, which will cut down on the number of function calls needed to do these vectored operations, which will hopefully increase performance. Also, Sean yesterday in his OFI update talked about some updates to the FI trigger support, triggered operations. And hopefully, as that matures, we'll be able to have a much more natural implementation of collectives through OFI using this. And also, GASNet's moving on beyond having a single endpoint communication model to being able to have multiple communication endpoints, and also multiple memory regions that are registered for RMA access. And as we've already talked about, hammered you on the head multiple times before, OFI has very good support for both of these, so we look forward to having a good mapping there. So just a grab bag of future work that we hope to do for OFI. We want to investigate more scalable communication. And one of those great features that are going to show up in OFI 1.5 is FI shared AV. That means if you have multiple processes on one node, they can all share one data structure for the address vector and cut down on the memory. Because we're going to start having like tens of thousands of nodes. That's a lot of memory to be taking just for keeping a list of addresses. Hopefully, we can also look at using some scalable endpoints to cut down on the amount of addresses we need to register. And the rest are just some basic things. We obviously want to make performance as best as we can. We want to support the next version of GASNet, definitely. And we have some other grab bag items like improving the current active messaging path. And then obviously, we want to support as many OFI providers as we can. So that's all I have. And before we go to any questions, I want to give special thanks to Paul Hargrove and Dan Bonachea from LBNL. They've put in a lot of time and effort to helping us improve these implementations, both the OFI and our native PSM, and I really appreciate them and their time. So with that, are there any questions?